Alright, so in this video, I'm going to solve the equation 1 to the power of x is equal to 2. So, before we even start solving this, if, let's say x is equal to 1, then I have 1 to the power of 1, which is equal to 1. And if x is equal to 2, then I have 1 to the power of 2, which is also equal to 1. And you can go even 1 to the power of 10 is still equal to 1. So you may be thinking, what possible value of x can make 1 to the power of x equal to 2? So let's try solving this. What I'm first going to do is start by taking ln of both sides. So I get ln of 1 to the power of x is equal to ln of 2. And ln is the same thing as the natural log. And the reason I took the ln on both sides is because it comes with a property that states that if I have something in the form ln a to the power of b, I can move this exponent b to the front, so this turns into b times ln a. So in this case, I have ln 1 to the power of x, and I can move x to the front. So I get x times ln 1 is equal to ln 2. And you may be thinking, we could just divide both sides by ln 1 and x would equal ln 2 over ln 1. However, the only problem with this is that ln 1 is equal to 0. And remember, anything divided by 0 is undefined, so this would be undefined. So we know that this equation has no real solution, but it could still have imaginary solutions. So to actually solve this, I'm going to use something known as Euler's formula. And basically what this formula is if I have something in the form e to the power of I times theta, this is equal to cosine of theta plus I times sine of theta. And I know to many of you watching this video, this may just sound like a bunch of gibberish, but just hang on. So let's say that theta is equal to 0, right? Say that theta equals 0. So now I get e to the power of I times 0 is equal to cosine of 0 plus I times sine of 0. Cosine of 0 is 1 and sine of 0 is 0. So I get this all is equal to 1. Now, what if we say theta is equal to 2k pi? And k is just a substitution for all real numbers. So now I get e to the power of I times 2k pi is equal to 1. Because all we did was we just substituted theta in for 2k pi into this same thing. So now, because this is equal to 1, we can remember our first equation, which we started with 1 to the power of x equals 2, we can substitute in this for 1, meaning I get e to the power of I times 2k pi to the power of x is equal to 2. So just think of this as 1. So I have basically 1 to the power of x equals 2. And now, with this, I'm going to take the ln, or natural log, on both sides. So I have ln e to the power of I times 2k pi to the power of x is equal to 2. So I'm going to now bring this x down using the property of natural logarithms. So I get x times ln e to the power of I times 2k pi is equal to 2. is equal to ln of 2, because if you take ln on one side, you have to do the other side. And now I can also move I times 2k pi to the front. So I have I times 2k pi times x times ln e is equal to ln 2. ln e is simply equal to 1. So I get x is equal to ln 2 over I times 2k pi. And now I'm going to multiply this by I over I. So I get x is equal to negative I times ln 2 over 2k pi, because I squared is negative 1. So this is my solution. Alright, so in this problem, I have a to the power of 3 plus a squared is equal to 392. So I obviously want to find the value of a here. So for my solution, I'm going to first start by rewriting my equation here. So I get a to the power of 3 plus a squared is equal to 392. And now I'm going to subtract 392 on both sides. So then these two cancel out, and this turns into a to the power of 3 plus a squared minus 392 is equal to 0. Now from here, I can rewrite negative 392 as negative 343 minus 49. And the reason I did this was because 343, this is something cubed, and 49 is something squared. And notice how we have something cubed, something squared. So I'm going to change the order of this. Actually, first, I should rewrite 343 as 7 cubed and 49 as 7 squared. So we have a cubed plus a squared minus 7 cubed minus 7 squared. Sorry, this is 0. And now I'm going to change the order to this to group the cubes and then group the squares. So I have a to the power of 3 minus 7 to the power of 3 plus a squared minus 7 squared is equal to 0. Now, here are two properties that we're going to use for this. So to start, if I have something in the form a to the power of 3, actually I should do x to the power of 3 minus y to the power of 3, this is equal to x minus y times x squared plus y squared plus xy. And now if I have something in the form x squared minus y squared, this is equal to x plus y times x minus y. So in this case, x is equal to a and y is equal to 7. We're going to first start by rewriting a to the power of 3 minus 7 to the power of 3 in this form. So this is going to be equal to a minus 7 times a squared plus 7 squared plus 7 times a, which is just 7a. And now I have this plus x squared minus y squared. This is x plus y times x minus y. So it's going to equal a plus 7 times a minus 7. And this is all equal to 0. Now notice how both of these terms have a common factor of a minus 7. So if I factor out a minus 7, I get a minus 7 times a squared plus 7 squared plus 7a plus a plus 7 is equal to 0. And this simplifies to a minus 7 times a squared plus 8a plus 49 plus 7, and 49 plus 7 is 56. So this is equal to 0. Now from here, I get two equations. I get a minus 7 is equal to 0, and I get a squared plus AA plus 56 is equal to 0. So for a minus 7 equals 0, I can add 7 on both sides. So these two cancel out, and I get a equals 7. And for a squared plus AA plus 56 is equal to 0, I can use the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, a is 1, b is 8, and c is 56. So I get a is equal to negative 8 plus or minus the square root of b squared, so a squared minus 4 times 1 times 56 all over 2a. And this is equal to negative 8 plus or minus the square root of 8 squared, which is 64, minus 4 times 56, which is 224, all over 2. And this turns to negative 8 plus or minus the square root of negative 180. And notice how you the square root of a negative number, so this will not work. So our only solution is a equals 7. So now to check, the original equation was a to the power of 3 plus a squared is equal to 392. So we have a equals 7, so I get 7 to the power of 3 plus 7 squared is equal to 392. Now, 7 to the power of 3 is 343, and 7 squared is equal to 49. So I have 343 plus 49 is equal to 392, meaning 392 is equal to 392.